The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
All right. So last time, what we had done is that we had looked at the first evidence for the particle-like nature of radiation. And that evidence was a photoelectric effect. The evidence was that what you had to have was a photon, or a particle of energy, a quantum of energy, a packet of energy in order to get an electron out. And that energy had to be at least the energy of the work function of the metal. And so for every packet you put in there, you got one electron out. All right? That's an example of the particle-like nature of radiation. But Einstein, he went on to show an even more convincing property of the particle-likeness of radiation, or a photon. And that is that what he did is he showed that a photon has momentum. It has momentum even though a photon doesn't have mass. Although a photon doesn't have rest mass, for those of you in the know in this area. Okay? And, having momentum, hey, that is very much a particle-like property, right? Because you know how to write down momentum. Momentum is mass times velocity. Hey, you got a mass in here. That's a particle-like property. Right? And yes, I am starting out with the lecture notes from number 4, which I didn't finish last time. Okay? So that's a particle-like property. But what Einstein showed was, from the relativistic equations of motion, what drops out from the relativistic equations of motion is the fact that a photon at a frequency nu has a momentum h nu over c. Okay? And because we know the relationship between nu and c, nu times lambda equals c, I can write the momentum of a photon as h over lambda. Okay? So if you have some radiation, this is the photon momentum here. So if you have some radiation at a wavelength lambda, that radiation, or those photons, have this momentum p, given by h over that wavelength. Now, that was a prediction from the relativistic equations of motion. And it took another 8-10 years or so before there actually was an experiment that demonstrated the momentum of a photon. And that experiment was called the Compton experiment. What went on in that experiment is that an X-ray beam came into some material, or some molecule, some atoms, and they could actually see the transfer in the momentum from the photon to the atom. Kind of like, in this website from the University of Colorado here. Hey, this is just a cartoon of what's happening, but here I got this photon gun, and I got this atom coming at me, and I can't move this fast enough. I'm going to get clobbered. Well, all right. You got a different computer than I got. Yeah. Oh, I have to push down in here. Okay. Well, if I get aimed here, well, these photons are coming at this atom coming at me, and boy, if I do it fast enough, hey, I can turn it around, right? Hey, I did it. Whoa, hoo-hoo. But now, of course, if I go and I lower the power, and come on. I got killed. Christine, I don't like your computer. Oh, wait, this. Well, Christine's going to try now. Oh, look at that. Oh, she's going to get it. She's going to get it. She's going to get it. Yay! 3 cheers for Christine. Oh, now it's something else. All right, this is going to keep going here. Right, you need more power there. Okay, there. Hey! Ah, got that guy. Fantastic. All right. And it's actually just this effect that was used by Steve Chu at Stanford and Bill Phillips at NIST, and Cohen and Tanuji, who provided some of the theory behind it. It's just that effect that they use to literally trap an atom in space. So how do you do that? Well, you take an atom, right, unsuspecting atom, and you bring in a laser beam, high-power laser beam coming out in this direction, and those photons transfer momentum, and they push that atom this way. But you're smarter than that, so you bring in a laser beam this way, right? And so you have momentum transfer this way and this way. Hey, you just trapped the atom in this dimension. And then you bring in a laser beam this way, bring in a laser beam that way. Hey, you trap the atom now in this dimension. And then you, what's that? Your dog. Well, that's not part of my lecture. No. All right. And then you bring in the laser beam this way, right? And so now you've constrained it in 3 dimensions. And so the atom is trapped in space by this photon pressure, by this momentum transfer, right? And this is called laser trapping. And these 3 gentlemen whose names I gave you just a moment ago for atom trapping, laser atom trapping, received a Nobel Prize in 1997 for this demonstration. But the other reason why this atom trapping, this laser atom trapping is really so important is because it's actually the first step in another experiment. It's the first step in producing a Bose-Einstein condensate. What this laser trapping does is literally to slow the atom down because, or to cool the atom, right? Because temperature and the velocity of the atom, the speed of the atom, are related. The slower the speed, the lower the temperature, right? And to produce a Bose-Einstein condensate, you have to have bosons, which you lower in temperature, and ultimately they condense. And the temperatures have to be on the order of microkelvin. And so this is the first step in producing that Bose-Einstein condensate. This will bring you down to temperatures of, say, a Kelvin or so, all right? And then there are lots of other techniques. There are a couple of other steps that bring you down to the microkelvin range. And then finally, you can get the bosons to condense. And one of my colleagues in the physics department, Wolfgang Ketterle, he was also received a Nobel Prize for the formation of the Bose-Einstein condensate. I actually think he's teaching a recitation section in 801. Maybe some of you have him. And you do? No, you don't have him? Okay. But you'll be able to meet him and talk to him. Question? I'm sorry? Fantastic. Has he told you about this yet? Oh, he went to a conference. Okay, all right. Well, you can imagine he's in demand. But you'll see him, right? I hope. Okay. All righty. So, very important effect here. So we've got radiation, which is exhibiting both wave-like properties and particle-like properties. And just in general, experiments where the radiation produces a change in the state of the matter such as the photoelectron effect. In photoelectron effect, the matter changes in the sense that an electron is pulled off of it. In those experiments, the radiation usually exhibits the particle-like behavior. In experiments where there is a change in the spatial distribution of the radiation, or where the radiation interaction results in a change in the spatial distribution of the radiation, well, that is when the radiation exhibits its wave-like behavior. And so it really is not appropriate to ask, is light or radiation a particle or is it a wave? The appropriate question to ask is, how does light behave? Does it behave like a particle or does it behave like a wave under particular experimental circumstances? And this, having both behaviors, this wave-particle duality of radiation, is not a contradiction. It just is the fundamental nature of radiation, of light. You may think it's a contradiction because, you know, in your everyday experience, you either see a wave or you see a particle, right? But that's your everyday experience, and there are parts of nature that you can't see every single day. And those deeper parts of nature, right, have different rules. And you have to be accepting of those different rules, right? And so it's not a contradiction in terms. It just seems strange to you just because that isn't your everyday experience, okay? It's the fundamental nature of radiation. Okay, well, not only is that the fundamental nature of radiation, but the wave-particle duality of matter is also the fundamental nature of matter. And that's what we're going to talk about right now. We're going to move to matter, particles. So matter, the particle-like nature, well, that is within your everyday experience. But it's the wave-like nature of matter that's not within your everyday experience. And so let's take a look at that. Suppose we did this experiment. That is, we had a nickel crystal. And these two atoms here are just two of the atoms on the surface of a nickel crystal. And we know the spacings between these two atoms in the crystal because we know the crystal structure of the nickel. That spacing is about 2 times 10 to the minus 10 meters. Well, naively, if you brought in a beam of electrons, right, particles, we know they have mass. J.J. Thomson taught us they were particles, they had mass. But naively, if you brought them in, you might expect these electrons to scatter isotropically. That is, that they would scatter equally in all directions, so that when they ultimately hit this screen here, this curved phosphor screen, and I changed the geometry here to a curved screen just so that it'll be a little bit easier to analyze the geometry of this problem, which we're going to do in a moment. You might expect this screen to be lit up uniformly at all angles. Well, this is exactly the experiment that Davison and Germer did in 1927, along with this gentleman, G. Thomson, George Thomson, son of J.J. Thomson, okay? And J.J. Thomson actually did an experiment a little different than Davison and Germer. I'm going to show you the Davison and Germer experiment here. But here's this same diagram that I had before, except that I made the nickel atoms a little bit smaller, just so that this diagram would be a little bit easier to understand. I cleaned up the diagram, but I kept the spacing between the two nickel atoms the same. And so Davison and Germer and Thomson came in, scattered these electrons, and looked how they scattered back. And lo and behold, what they saw is that these electrons seem to scatter back at a preferential angle. the angular distribution wasn't isotropic. And instead, it looked like the electrons scattered back at a pretty well-defined angle here, 50.7 degrees. And not only did they scatter back at that angle, but they also scattered right back at themselves, right? Back scattered this way, so this scattering angle is 0 degrees. And under some particular conditions, the electrons also scattered at a larger angle here, right? But the bottom line is that the scattering pattern wasn't isotropic. There was a bright spot, lots of electrons scattered at this angle. A dark spot, no electrons scattered at this angle. A bright spot, dark spot, bright spot. Hey, this looks like interference phenomena, right? Just like the two-slit experiment. Bright spot, bright spot. Constructive, destructive, constructive interference, back and forth. That was their observation. So, how do we understand that? Well, it's looking like these electrons are behaving like waves. So, suppose these electrons are coming in. So we have this constant stream of electrons impinging on our nickel crystal. Well, what's happening here is that when these electrons are reflecting back from the individual nickel atoms, these individual nickel atoms are kind of functioning like those little slits we saw in the two-slit experiment. That is, that they're scattering back as a wave. These electrons seem to be scattering as a wave, so isotropically in all directions. This semicircle around each one of the atoms, and I only show you two atoms here, each semicircle is the maximum of the wave front. It's the crest of the wave front. And then as time goes by, of course, these waves propagate out, and then another wave front, another wave maximum appears, and the distance between these two maxima is, of course, the wavelength. Right? And as time goes on, they scatter further, right? And as time goes on, they still scatter, and they keep propagating out until they reach the screen. And lo and behold, on the screen, you see a bright spot, dark spot, bright spot, dark spot. Okay? Interference pattern. So let's analyze this. So here's the diagram again. I just moved it over and cleaned it up again. I want you to look at this spot right in there. Hey, that's where we've got the maximum of a wave scattered from atom 1 at the same point in space as the maximum of waves scattered from atom 2. Constructive interference. Here's another point of constructive interference. Here's another point of constructive interference. Everywhere along this line, we have constructive interference, which results in a large intensity right at this scattering angle here, a bright spot. And we already know the condition for constructive interference, and that is, in order to get this constructive interference, the difference in the distance traveled by the two waves that are interfering has to be an integral multiple of the wavelength lambda. Okay? Now, I use the term d instead of r, but it's the same thing for the condition for constructive interference here. And if you went and analyzed what the difference in the distance was for this constructive interference along this line, you'd find it was n equal 1. So the difference in the distance traveled is 1 lambda. And if you looked at the points of constructive interference along this line that led to this bright spot, the difference in the distance traveled would be 2 lambda. So this is our second order interference feature, our second order diffraction spot. And if you looked at it along the center here, normal to the crystal, that would be the 0 order spot. d2 minus d1 is equal to 0 lambda. All right, so that's what it looks like is happening. Now, what we're going to do is we're going to actually analyze this geometry a bit more. We didn't do so in the two-slit experiment. We could have. We didn't. We're going to do it here. And what we're going to be after is if these electrons are acting like waves, then they have a wavelength. And we want to know what the wavelength is. Davison and Germer wanted to know what the wavelength is. And we're going to use this scattering angle here, theta, this angle from the normal to where the electrons are scattering, that angle theta. We're going to use that information, theta equal 50.7 degrees, to back out the wavelength. And we know what the condition is for constructive interference. We just talked about it. Here it is, d2 minus d1. That's the wavelength that we're after in this analysis. Now, what's d2 here? Well, d2, the length of this line, d2, is the distance that the wave, which scatters from electron 2, travels from electron 2 to the screen. d1 is the distance that the wave that scatters from atom 1 travels to the screen. Okay, that's what d2 and d1 are here. Now I'm going to draw a perpendicular from atom 1 to this line d2. There's my right angle. Now, you can see then that this leg of the triangle is d2 minus d1. The difference in the distance traveled. It's this quantity here. That's going to be important. Now you've got to convince yourself that this angle right here in the triangle is the same as this angle, the scattering angle. All right? You can convince yourself of that pretty easily. So now we got this well-defined triangle. We know one length of it. We've measured the angle theta. And boy, d2 minus d1 is something that we'd like to know. So let's do a little geometry. So the sine of theta, the sine of this angle, is equal to the opposite length, which is d2 minus d1, divided by A, this distance between the two atoms in the nickel crystal. So we got two equations. This is the equation that in theory should obtain for constructive interference. This is the equation that we set up given the particular physical geometry of our problem. Hey, these two d2 minus d1s better be equal to each other. Okay? So we got n lambda is a sine theta. Let's solve for lambda. We can do that. That's a sine theta over n. So we already know what theta is. We know what A is. What's n? Well, n is going to be 1 because this is the bright spot that is closest to the zero order spot, which is always present at the normal angle there if you're coming in at normal orientation. Okay? So n is equal to 1. So I can plug things in. And when I do that, I find that the wavelength that I predict is 1.66 times 10 to the minus 10 meters. Okay, so we got this wavelength. Now, before I go on, I just want to point out that this geometry of the problem that I set up here is identical to the geometry in a technique known as X-ray diffraction. X-ray diffraction doesn't use electrons coming in, but it uses X-rays, photons. And it is a technique that's going to be important to you if you do any kind of science involving materials or biological systems. And it's important because X-ray diffraction allows you to get the structure, to determine the structure, in particular of proteins, crystal proteins. You crystallize the protein, and you use this X-ray diffraction to get out the structure. And the reason why you want the structure of the proteins is because the structure gives you a hint as to what the function of the proteins are. So in the use of X-ray diffraction, we don't go and calculate what lambda is, right? We already know what lambda is in X-ray diffraction, right? We know the wavelength of the incident photons, the X-rays. What we don't know in the technique of X-ray diffraction is we don't know the distance between these two nickel atoms, or between the atoms in an unknown structure, right? And so in X-ray diffraction, we know the wavelength, and we can figure out what order it is, and we measure the scattering angle, all right? And we use that to determine the distance between the atoms. And in that way, we back out the structure of the sample.
Would you have gotten the same wavelength for the electron if you plug in its mass to the de Broglie equation?
Yes, we're just going to get there. Right, we're going to do that just right. Yeah. Okay? All right, so same geometry here. So now this experiment of Davison and Germer was really an important one, because just 3 years before this, there was a prediction for what the wavelength of particles ought to be. And that prediction was made by this gentleman, Louis de Broglie, right? And, hey, in his PhD thesis, no less, what Mr. de Broglie did is that he looked at the relativistic equations of motion that Einstein wrote down. The relativistic equations of motion that Einstein used to propose that a photon or radiation with a wavelength lambda had momentum p. Well, he took those same equations, right? And he said, well, you know, these relativistic equations of motion apply to matter just as well as they apply to radiation. So therefore, if you have matter, or therefore, if you have radiation with a wavelength lambda, you then have this momentum p for the radiation. This is what Einstein said. But he turned it around and said, well, if you've got matter with a momentum p, well, that matter ought to have a wavelength lambda. Okay? He turned around Einstein's equations of motion and proposed that the wavelength of a particle be given by h over p, where, of course, p here is the mass times the velocity. All right? Fantastic. What a great PhD thesis, right? I'm impressed. All right, now, let's see how well that, as you can imagine, let's see how well that predicts the wavelength that de Broglie, the wavelength that Davison and Germer actually measured. All right, so we know we have 54 electrons coming into this nickel crystal. That's their kinetic energy. That's 1/2 mv squared. Kinetic energy can also be written in terms of the momentum. The momentum is p squared over 2m. You can convince yourself of this. This is a good thing to know for doing these problems, that the kinetic energy is p squared over 2 times the mass of the electron. And so if you solve that, what you get for the momentum of the electrons is 4.0 times 10 to the minus 24 kilograms meters per second. And now I can take this momentum and plug it into the expression for de Broglie's wavelength, 6.6 times 10 to the minus 34 joule seconds over the momentum, 4 times 10 to the minus 24. Hey, what do I get? 1.7 times 10 to the minus 10 meters. Absolutely the same as experiment, right? So de Broglie made a prediction, and a few years after that, experiments demonstrated that de Broglie was absolutely correct in his prediction. All right. So what do we got here? Well, hey, we have matter, particles, exhibiting wave-like behavior. And those particles can be measured to have a wavelength which actually agrees with a prediction, some theory, the de Broglie wavelength. And we also have another phenomena here, which I really enjoy, and that is Davison and Germer and George Thomson. Hey, they demonstrated that electrons behave like waves, right? And what did J.J. Thomson do? Father of George Thomson? Well, J.J. Thomson, right, demonstrated that an electron was a particle. So here we have both the father and the son talking about seemingly opposite behavior, but they're both right, right? How often does that happen? That's really pretty. I think that is really amazing. Okay. But if matter is wave-like, right, if electrons can be represented by a wavelength, then what about your wavelength and my wavelength? You know, we should have a wavelength. Okay, and we do. Okay. And just briefly here, let's talk about what the wavelength is of a baseball pitched by Curt Schilling, you know, at 90 miles per hour. All right. What is that wavelength? Well, baseball is 5 ounces, 90 miles per hour. You can calculate the momentum. It's in your notes there. We will calculate here the wavelength. And what you're going to find is that it's 1.2 times 10 to the minus 34 meters. Okay. Hey, that's pretty small, right? What's the size, the diameter of a nucleus? 10 minus 14. Right, that's a good number to know. Here we got a wavelength that's 10 minus 34 meters. Is that wavelength of a macroscopic size object going to have any consequence in our world? No, absolutely not. Why? Because in order to see any effects from this wavelength, from this small wavelength, we're going to have slits or atoms that are going to be on the order of this close together. But there's no way that we're going to have 2 nickel atoms that are this close together, right? Or 2 slits in a 2-slit experiment this close together. And so for macroscopic objects, the wavelength, the wave-like properties have no consequence in this world, right? And that's simply because the mass is too large. It makes the wavelength too small to have any effects in our everyday lives. Okay? All right. And it's actually, yes? Okay. Well, right. They're actually coming in as waves. They're behaving as waves. So remember my beach picture? You know, I drew them coming in, you know, like a circle. But remember my picture of this barrier here on the beach, right? And then I'm laying here on the sand. Right, and then the waves are coming in. Here's blue, right? These electrons, as they're coming in, right, really need to be thought of as these kind of plane waves. I drew them as kind of just particles, right? But you have to really think of them as plane waves. and that they are reflecting off of these two atoms in the way that I just explained. Okay? Another question? Right. The thing is that you can't get that velocity slow enough to make the wavelength be large enough to be of consequence. If you could, then you would, right? You would see the wave-like behavior. But you can't, practically speaking, get it to that extent.
Measuring the wavelength of a baseball going 90 miles an hour, would you have to also account for the fact that when we're going through space, it's really, really very, very quickly? Or is that all taken care of in the fact that the point at which you're observing will observe that wavelength? And
Well, are you asking?
I'm asking, do you have to account for the fact that we're hurtling through space really quickly, or is it the wavelength have to do with where you're observing the baseball from?
No. In this particular case, anything that's so massive, any smaller effects like what you're talking about, exactly the point of observation, is not going to have an effect on anything that is so massive. Okay? Pardon? Yes, it will. Your point of observation will have an effect, yes, on your interpretation of the experiment. If you are talking about something that has a much larger wavelength, right? Absolutely, right? In high energy physics experiments, for example, right? No question. Okay. All right, so it is just this observation here of the wave-like behavior of electrons, of particles, that led to the interpretation then, or led to the realization that maybe you have to treat electrons as waves, or maybe you have to treat the behavior of electrons as wave-like behavior, all right? And that is what this gentleman, Schrodinger, did, right? He said, well, you know what? Maybe this gave him an idea, right? Maybe what's wrong is that in an electron in an atom, maybe what's wrong is that I can't treat that electron as a particle. Instead, what I have to do is I have to treat it as a wave. I have to treat its wave-like properties. And it was that impetus that led him to write down a wave equation of motion, an equation of motion for waves. All right? He realized, or he was guessing at the moment, but he thought, well, maybe in the case when a particle, a microscopic particle, has a wavelength that is on the order of the size of its environment, well, in that case, maybe the wavelength has an effect, makes a difference. So, for example, in the case of the electrons, we had a wavelength I calculated there of 1.7 times 10 to the minus 10 meters. Hey, that's a wavelength that is on the order of the size of the environment of the electron, which is on the order of the size of an atom. Maybe in that case, I got to pay attention to the wavelength. The reason you and I, we don't have to pay any attention to our wavelength is because our wavelength is 10 to the minus 30 meters or so, right? And that's much, much larger than the size of the environment. In this case, we don't have to pay any attention to our wavelength. But for an electron in an atom, uh-oh, we got a problem here, right? So what did Schrodinger do? Well, Schrodinger said, I got to write down a wave equation, an equation of motion for matter waves, And what is that equation of motion? Well, that equation of motion is H hat operating on psi, and it gives us back an energy, E, times a psi. Okay, so what is this? Well, psi here is a wave. I am somehow going to let my electron in an atom be represented by psi. This is going to be a waveform. This is going to be a wave function. I'm going to let my electron be represented by the wave function. Exactly how it's going to be represented by the wave function is something that I'm not going to tell you quite yet. All right? But it's going to represent the electron. This energy here, that energy is going to turn out to be the binding energy of the electron in the atom. Okay? This thing here, well, this thing is called the Hamiltonian operator. That Hamiltonian operator is specific to a particular problem, and we will look at the Hamiltonian operator for a hydrogen atom. But this operator is operating on psi, and it gives you back a psi, the same function, multiplied by a constant. That constant is the binding energy. Now, you think, all right, well, let me just cancel this and this, right? But you can't do that, right? Because this is an operator. This has got some derivatives in it. It's operating on psi, gives you back the same function times a constant. All right. So now, how did Schrodinger actually derive this equation? Derive, so to speak. Well, what he did is to just guess at a wave function. All right? So we're going to use a one-dimensional wave function. He's going to say, let me represent my electron by psi of x equal to 2a times cosine 2 pi x over lambda. Okay? That's going to be my wave function. Why not? And then he said, well, what I really need here is I need an equation of motion. I need to know how psi changes with x. So if you wanted an equation of motion, if you want to know how psi changes with x, right, what would you do to psi? Take the derivative. Hey, let's take a derivative. Derivative of psi of x with respect to x, that's going to be equal to minus 2a times 2 pi over lambda times sine of 2 pi x over lambda. That's an equation of motion. Now, this is actually a kind of an equation of position, but it's telling us how psi changes with x. Right? All right. But now, since that gave us some information of how psi changes with x, how would we figure out how the rate of change, how will we get the rate of change of psi with x? Second derivative. Let's take the second derivative of that. Second derivative of psi of x with respect to x. All right, that's minus 2a times 4 pi squared over lambda squared times cosine 2 pi x over lambda. Hey, that's pretty good. But now, what do you see in this equation? Psi. Absolutely. You see what I started with. Yeah, it's recursive, right. You see the psi of x here. So let me write that equation in terms of the original function. Right? Second derivative of psi of x with respect to x minus 2 pi over lambda squared times psi of x. Okay? Hey, that's pretty good. You know where I'm trying to go? I'm trying to derive, so to speak, Schrodinger's equation. You can see it's not very hard, right? Okay. Ah, yes. Now, this equation right here, this equation is just a classical wave equation. The only thing I've done so far is take derivatives. I have done nothing else, right? I just took derivatives. It could represent any kind of wave. You know, there's nothing quantum mechanical about it. But here comes the big leap. And the big leap that Schrodinger made is that he substituted in here for lambda, he substituted in the momentum of the particle. In other words, if this is a wave equation, and that wave has some wavelength here, lambda, he said, well, if this is a wave equation for a matter wave, well, then I better get the momentum of that particle in this wave. Right? And he knew how to do that because de Broglie told him how to do that. De Broglie said lambda is equal to h over p. All right? Hey, that's pretty good. So what can I do here? Well, what I can do is I can rearrange this and write this in terms of the momentum of the particle. All right? So, second derivative of psi of x with respect to x is going to be minus p squared over h bar squared times psi of x. Now, let me explain what h bar here is. H bar is a shorthand way of writing h over 2 pi. If you don't know it already, you should know it. You're going to need it. Okay? That's h over 2 pi, so this is h bar squared. So now what do I have? Now I have a matter wave. I have an equation of motion. I have something that tells me how psi moves with respect to x, the rate of change of psi with x. And I have the momentum of the particle buried in here. Okay? From this form, I'm going to get to that. All right? And I guess I'm going to get to that next Wednesday.